So in this lecture, we're going to introduce the concept of characters, which come from representation theory, and are going to be tools we use to answer some of the questions we have about representations. So here's the definition. Given a representation, of a group into a group of matrices. So here we actually do want a fixed basis. So we actually do have matrices. You can define a function called its character. It's usually denoted chi. It has domain G. It has codomain the underlying field. And chi of G is just defined to be the trace of the associated matrix. And so recall that a matrix has n by n entries, n by n matrix. So this is the sum of the diagonal entries in the matrix. So that is the definition of a character. In general, a character is any such function coming from any representation. Right now it seems like it depends on the basis, but we'll see a choice of basis because you need an actual matrix representation. But we'll see in a moment that isomorphic representations are going to have the same character. And so characters are defined up to equivalence. And the key to that is to just realize that for any two matrices, the trace of A times B is actually equal to the trace of B times A. And why is that? Well, what is the trace of a matrix? By definition, it's the sum of the diagonal entries. But what is the diagonal entries in the product? Well, by definition, that's the summation k goes from 1 to n, aik, bik. You can check that the trace of b times a is going to be almost the same thing if I swap the role of I and k for right now. You would end up seeing that you get this formula. And so the only difference is commutativity and changing the order of summations. So these two really are the same. And so in particular, if I take an invertible matrix P and GLNK, and I look at P inverse phi of GP, I define that to be a new representation. Then the trace of psi of G, that's just the trace of P inverse G times P. If I treat this as A and this is B, then by that multiplicative property, that's equal to the trace of phi of G, P, times P inverse. P times P inverse cancels, and I just get the trace of phi of G. So we see that the trace of these two representations is the same for every group element. And so particular, the corresponding characters are the same. So equivalent representations have the same character. So if you switch to studying characters instead, you can now simplify your problem of classifying irreducible representations, you're just looking at the characters. And now you don't have to worry about whether or not things are equivalent or not, because, well, you just look at whether or not they have the same character. Although we haven't quite proven the opposite thing yet, that if they have the same character, they have to be equivalent. That also turns out to be true, but that's going to take a little bit more work. Note this actually means that the notion of character is actually well defined. For any representation or any G module. Note here, my point is that you haven't picked a basis yet, but what you have to do is choose a basis, then you actually get a representation as matrices, and then you get the associated character using the trace. And the point is, if you chose a different basis than from linear algebra, you get a different, if you chose a different basis, you would have gotten an equivalent representation up to change of basis. But as we just saw, it would give you the same character in the end. So even though we defined it in terms of the sum of the diagonal entries, you can actually get the direct formula. I mean, it's actually an invariant of the module itself. So we're finally at the point where I'm going to just go ahead and start saying that we're working with the complex numbers. And in this case, it's also well known that a trace of the matrix is actually the sum of the eigenvalues. Including the multiplicities. And there are places we might need to use that fact. And so that gives another way to define the trace without respect to a basis, because the definition of eigenvalue doesn't care about bases. However, this fact relies on working over an algebraically closed field because, well, it relies on the fact that over an algebraically closed field, you're guaranteed to be able to write your matrix in a nice form with respect to the eigenvalues, where Bi has some eigenvalue down the diagonals, and then just one on the off diagonal. So if you've taken an advanced linear algebra course, you might have seen this before. It's called Jordan decomposition. So of course, this isn't an advanced linear algebra course, so I'm not going to prove that fact. But this is a known fact that if you're working over an algebraically closed field, so that the characteristic polynomial always splits, then every matrix can be written up to similarity as a block diagonal matrix consisting of these almost diagonal matrices. And so that tells you the trace of this type of matrix ends up just being sums of eigenvalues, including the multiplicity. So that's some of the information you can get from what we have so far. Finally, the other information you can get is, suppose we have a character. Now let's conjugate a group element and compute the character with respect to this conjugate. Well, then by the same logic we already had, remember this should technically be phi of G inverse HG. So we eventually get lazy when we write the group elements when we actually mean this particular representation, or I mean trace here. It's the trace of the corresponding matrix. It's a representation, so phi is a homomorphism. Again, using this rewriting trick, trace of AB is equal to trace of BA. These two matrices cancel, and we get chi of H. So what this tells you is that if two elements are conjugate, then chi of H is equal to chi of H prime. So equivalent representations that give rise to the same character, and if you actually want to compute the character, you only really need to compute the character values on one element of each conjugacy class, because it's constant on the conjugacy classes. And that tells you all the information you need to compute the character in general. So in general, they call these class functions. So we're going to let C of G be the set of conjugacy classes. And you've got the equivalence relation coming from conjugation. So a class function is any function f from G to K with f of x equals f with x equivalent to y, implying that f of x equals y. Note, whenever you have this fact, it's equivalent to just defining a function from the conjugacy classes to K. Because if I know what value it takes on each conjugacy class, then I know what value it takes on each element of the conjugacy class, and vice versa. So to illustrate what we've learned so far with an example, we'll take the group S3. The conjugacy classes of the symmetric group correspond to integer partitions. As we've seen, there's the conjugacy class corresponding to the identity permutation, the conjugacy class corresponding to 2 cycles. So this is the integer partition 1, 1, 1. These are cycle types you might remember: a 2 cycle and a 1 cycle, or a 3 cycle. So 2, 1 is the conjugacy class consisting of all 2 cycles only. And 3 is the conjugacy class consisting of the 3 cycles. Of course, for the purposes of the table, I'll stick with the familiar notation with the partitions. So these are our conjugacy classes. So given any any representation, we can look at the characters on these conjugacy classes. So let's look at some representations of S3. Let's look at representations from S3 to C itself. Well, there's the obvious trivial representation, which sends every group element to the identity. And remember, this is a 1-by-1 matrix, so in this case, the trace is just the element itself. In general, the character of a one-dimensional representation is the one-dimensional representation. And so the value is all 1 on each conjugacy class for this particular representation. Another representation we've seen in this course for the symmetric group is called the signature representation. It's -1 to the, we'll call it k. So here we have to remember, if you write sigma as a product of transpositions, then the signature is -1 to the k. And it's a theorem that any two ways of writing sigma as a product of transpositions, if I write it as another product with m transpositions, then m is congruent to k mod 2. And so that you actually do get the same power of -1. You're either going to get +1 or -1. It's always going to be the same answer. So this is the sign representation. It's also one-dimensional. And of course, the identity element is a product of 0 even cycles. Any 2 cycle is a product of exactly 1 2 cycle. And a 3 cycle is always a product of exactly 2 2 cycles. So you can see that this is the character table or the character values of the sign representation. Now, of course, if you look at the vector space of all class functions, well, that space has dimension 3 because there's 3 conjugacy classes. And so far we have that the characters generate a 2-dimensional subspace. And so the question is whether or not there's at least one more representation. If there's one more representation, a 2-dimensional or 3-dimensional, some other dimension, then there would be at least one more character, and that would give you one more row, and that'd give you a third class function that's linearly independent from these two, and therefore you would have 3 linearly independent class functions, which would give you another basis. So from this theory so far, we can already see that there are at most 3 irreducible representations of S3. In another lecture, we will actually be able to determine what the third one is, but we don't have that information. Well, technically we can. You can use S3 acting on itself to actually figure this out.